Well, welcome back. So in this presentation, I'm going to give you some of the basic principles of caching, and then we'll be thinking about um, an analogy to how this caching works, and then finally in a third presentation, we're going to get into the nitty-gritty details. So let's start at a fairly high level, just thinking about the principles of caching and the very important concepts of what we call hits and misses. All right, so we've been looking at this notion of the memory hierarchy. And a cache is basically a smaller and faster storage device that acts as a staging area for some of the data in the larger, slower device further on down in the cache, in the hierarchy, excuse me. And so the fundamental idea here is that for each of these levels K, the faster, smaller device at some level serves as a cache for the larger, slower device at level K plus 1. And so why do these work in our case? And it's all because of this notion of locality that I went over in the previous presentation. So programs that tend to access data at level K more often than they access the data at level K plus 1, if those programs exhibit locality. So this means that the storage at some lower level can be slower because once it's moved up to an upper level, then the machine is able to access it there much more quickly. Now, we're going to really concentrate on this part of the cache. I'm going to mention some of the other levels and some other types of caching in this presentation, but generally speaking, for the rest of this course, we're going to concentrate on this area from main memory up through the level 1 and level 2 and level 3 caches. And in fact, we're really going to think of all of these two as the same thing. We're just going to call that cache, um, and treat each of these levels as the same thing. So so we're going to think of this in terms of our programs have come into memory, and now we're going to be using the cache in a particular way. Now remember, this is smaller than main memory by quite some amount, and we have to keep that in mind. So now let's look at this with this separate type of a picture, which I did bring up previously about how the Intel Core i7, which is a very typical multi-core processor, how it is designed. And so in there, here's our registers, and there's registers for each core. And then there's the level 1 and level 2 cache for each core. Now you notice with level 1, there's a separate cache for the instructions. The instructions often have good spatial and temporal locality. Most programs you'll look at, this will be the case for the instructions themselves. The data is a different matter, and that's the thing that we're going to learn more about, how we have to make sure we set up our programs properly to make sure that they have good spatial locality. And you've already seen a little bit of this. So then the level 3 cache here is stored by all the cores. This can be useful if you've written a parallel program that's using all the cores to access, say, a large array of data. Then the whole thing might be stored at this level. And then here's our main memory. So that corresponds to this level of the hierarchy. I've only shown the top level of the hierarchy here. And then here's the other portions there. And then something to note, the typical sizes of these of a Core i7 are these here, so that our L1 instruction cache and D cache will be about 32 kilobytes, which isn't a lot, but we'll kind of see along the way why this isn't much bigger. There are reasons. In order to keep it fast, in order to be these access times to be about 4 cycles, we need to keep it small. And we'll see that when we get into the nitty-gritty details later on. And then level 2 cache tends to be a little bit bigger, and level 3 cache a little bit larger. But that does, the size really is a direct relation to how fast you can access it. And so that's why these access times go down as we go down the cache here. Now, typically a block size for this sort of a processor might be 64 bytes. Some of them are 32. I'll use examples with both of those going forward. So this is a general outline of how a CPU organizes its cache and main memory. Now let's just get to some really basic concepts of how this works. So here I've depicted up here a cache with 4 what we call blocks of memory. Now, these blocks are larger, and we move the data between main memory and cache. Now, we keep the same block size in main memory as we do in cache, and data gets moved and copied in block-sized transfer units. Now, I mentioned in the last slide 64 bytes. Often they're 32 bytes. That says kilobytes. I'm gonna just fix this while you see me do it, because it's bytes. Blocks are 32 bytes. So I'm just gonna fix that right now. All right, so now let's see if we can start this over again from here. So we copy in blocks-sized transfer units, which are bytes, 32 or 64 bytes. Now, so these blocks, you see, there is a reason why these are lined up in this way, and we'll talk about this going forward. So suppose that in our program, we had a set of instructions that was in this block in main memory. Then as we access the first instruction, we will actually, which will be in fewer bytes, 3 to 5, right? We'll bring up the whole 32-byte block into cache. And then what happens from there going forward is the next few instructions of your program can actually be accessed directly from cache at that point. And then eventually you will need more instructions, and those can be brought up into cache. Now, your program might also be accessing some data, and that might be at a block a little bit further down here, for example. and that then can be requested and then brought up into the cache. And so this is the general idea, is that block-sized chunks are moved as opposed to individual data elements from memory. So not just one integer, but 32 bytes worth. So 8 integers at a time, for example, might be brought in. But it's always just based on what's in what you accessed and where it happens to be in memory. This blocking is a fixed pattern that we're going to talk about and see quite often over the next couple of presentations. So there's some very important concepts associated with this. One of them is called a hit. So if you request, if the program needs a data element or an instruction that is in block 14 and it's in the cache, excellent. Now we can access that straight away, and it's called a hit to the cache. Now, we could also have a miss. So perhaps we want to get the data that's in block 13 down here. And you see 13 is not in cache right now. And that would be a miss. And so it's not in the cache. We'd have to request it from memory, fetch it from memory, and bring it up. And so that's the notion of a hit. I mean, a miss. Now, since it wasn't in cache, we have to figure out where it is going to go in cache. And I don't know if you've noticed a pattern here, but the way I've been doing these requests and showing them move up into cache, it's based on a mapping. So these blocks here can go in this place in cache. These blocks here can go in this place in cache. These blocks here in this place, and these blocks here in this place. This is always smaller than our main memory by a large way. That's what these dots are indicating, is it's, main memory is even bigger. So when we choose to place a new requested block from a miss into the cache, there has to be some sort of placement policy. And in our systems today, these memory blocks are mapped like this to a set of cache blocks. And our cache can look different than this very basic way that I'm showing it here. So we'll see a little bit of a difference between how we decide where this mapping is. But this mapping is fixed, it's set, and it never changes in our computer. So there's also something called a replacement policy. So which of these will get evicted? So what we've been saying here is it's got to be this one that maps in here. Now we'll start seeing where we're going to, in our cache, grab some extra space here so that maybe we wouldn't have had to evict the one that was in here. But at some point, there is always some policy in which you have to decide which block up here in this part of your cache is going to get evicted to make room for a new one that's needed because of a miss. And so we'll see what some of those policies are in more detail later. Okay, so another type of miss is what's called a cold or a compulsory miss. These happen because your cache is empty. These happen at the very beginning of your program. When you first execute an instruction, then the block containing that instructions and the ones after it will get brought into cache. So this is called a cold miss. Now there's also something called a conflict miss. And so in that case, you're limited to what blocks are going to go up and where. And so we were talking about this, right? That we've mapped these in a particular way here. And so then that particular mapping here is saying that a block at level k plus 1 must be placed in the block I mod 4 at level k, because in this case, this is memory. We're calling that level k plus 1. Cache is at level k. And we happen to have a total amount of cache for 4 blocks only. And so we've taken a main memory here and just done its block size modulo 4 in order to say where in cache it's going to go. This is 0, 1, 2, and 3 in terms of cache blocks. So that's the particular mapping that's going on there. So conflict misses occur when a bunch of data objects all map to the same cache level. And so for an example here, if our code kept accessing block 0 and then 8, and then 0 and then 8, for some reason, this would probably be likely due to a poor spatial locality. So it just kept accessing these 2 blocks, and we only had this one place for them. Then we would keep missing. We would miss when it first brought in block 0, and then we'd miss when it had to bring in 8, and then it would miss when it brought 0 back in, and so on. And so this wouldn't make for a very good exploitation of locality at all. And so the poor locality is causing an issue. So poor locality often causes these conflict misses. And then there's another interesting kind of miss that can happen, and that's called a capacity miss. So suppose that our program was exhibiting pretty good spatial or temporal locality in that these were the blocks we were accessing. But maybe we were accessing data over and over again, or we were looping in a program that had a whole bunch of instructions, so it kept going back and forth, or it kept going back around. In that particular case, if our code keeps accessing these blocks, these 8 blocks, but we only have 4 in cache, then what happens is we keep having conflict misses because our code is accessing more blocks than the capacity of our cache in a short amount of time. And so this set of active cache blocks that's being accessed a lot in a short amount of time is called the working set of a program. And so some programs that are using large amounts of data, for example, might have a working set that's larger than its cache. And when this kind of thing is happening, there are different things you can do, but it's a very bad thing. It ends up making your program run slower than you really would like. And so you have to be cognizant of this. Sometimes you have to go to a bigger machine. Other times you have to turn off all the other programs running on your machine so that you can get your work done if you end up with a program that's using lots of data. Okay, so to summarize this now, we have the notion of different types of cache misses. Our cold misses, just because when you first start a program, you're going to bring your first few blocks into cache. We can have these conflict misses where we're where we don't have good locality for some reason, and we keep having to bring blocks in and out. And then this notion of the capacity miss, where your program's working set of active blocks is larger than the cache on your machine. So now, just as a little bit of an aside, caching is this really fundamental aspect of oops, that's like coming and going. But anyway, that says caching is very fundamental in our hierarchy and throughout our computer. And so here we see registers and our L1 and L2 cache that I've been talking about. We're going to talk about address translations in a little while, and so there's a little bit of buffering that happens for those. But there's some very interesting things, like chapter 9 of your book is all about virtual memory. And in reality, when you're running a pretty large program, you often don't have the whole program in main memory. And so part of it is being cached even onto our disk. Memory itself has a little bit of a buffer in the memory controller. When we're accessing files on disk, there's a little bit of a buffer in there that caches up some of the data before moving it up. And then at the lower levels, oops, sorry about that. The network will buffer parts of files that it's sending over. In your browser, there are web pages that get cached onto your machine so that they can be read more quickly when you access them often. And then also for web pages, there's a lot of servers all over the world that will cache up pages so that there's a shorter distance for you to go get a new page than where it physically is located on the server. So this is a real interesting way of using caching to our advantage that you aren't aware of, but you've been doing it all your lives whenever you do web surfing. And, pages appear instantaneously. It's because they're probably cached up somewhere besides the server they came from in the first place. Okay, so now to summarize all of this, last time I talked about this speed gap between how fast our CPU can operate and how much slower it is to access memory and then mass storage after that. And that gap is still sort of widening because of the effective speed of our CPUs. But now, if we think about this idea that our programs, if we write them well, exhibit locality, then the memory hierarchy, which bases itself on this caching, can effectively close this gap between CPU speeds and mass storage by making sure we have a fair number of hits. And we get those hits because of the locality. They're the next thing we're likely to access in the block is in cache, because when we bring things up, we bring them up as a block. And we do, however, have the notion of cache misses in the form of cold misses, conflict misses, and capacity misses. And so our job when we're trying to write our programs is to try to make sure that we have as few of these sorts of misses as possible. So poor locality can cause these conflict misses. Sometimes our programs just aren't suited for a particular machine we're running them on, and that is the cause of some of these capacity misses. So in the next presentation, we're going to get into far more details about how this is really done on the machine. So, so stay tuned for that, and fire up that video next.